All right. Hi, guys. I'm Christina Martinez. I'm the Sophie mentor for IEEE, and I'm going to talk to you guys about voltage division, but also a couple of other concepts that are pretty important and key to electrical engineering. So, who am I? Still trying to figure that out. I'm a senior at Cal State Long Beach. I also am interning at Northrop Grumman. This is my 6th year there ish. No, just kidding. It's gonna be my 5th year, but I start full time in about 2 months. But I also mentor high school students and enjoy music. All right, so this is the agenda for today. I'm going to go over voltage dividers, but also what happens when the current source needs to be included. Also, just current dividers, node voltage method, and mesh current method. These are all pretty key concepts for EE211. I had Professor Ari, who I think is back now, but he's pretty good. So a lot of the examples and stuff are directly from his exams and his work. So voltage dividers, why even? They have a large amount of practical applications. They reduce voltage just to a source value to something that is known. But so why? I mean, it's mainly just like large to small value. It's like what you want it to be. But so voltage dividers are pretty fundamental and probably the most common thing applied to circuits, but they're also used in potentiometers, variable resistors, and are used to create reference voltages. But as well as in everyday life, you see them in to be able to adjust radio stations, measure position of joysticks, and also level shifting, which is involved with microprocessor usage, because usually the microprocessor is a larger voltage than the sensors that are being used for the microcontroller. And so I was going to do an example problem for voltage divider. This is directly from Ari's class. So let me go ahead and switch to my iPad to walk it through with you guys. Hold on. Okay, does everyone see the screen? Is that
Yep,
a yes?
we can see the screen.
Okay, cool. All right, so the example problem is involving the output of having 4, 2, 1, and 0.5 voltage. In this case, I load is equal to 0. And so you can do, in this case, 1 milliamp as the current for the whatever it is that you desired. And so you want to have this type of circuit layout, which has resistor 1, resistor 2, resistor 3, and so on, but also have the voltages being used pointed out at the end because that's what you're mainly looking for, as well as the common ground. And so to start out the math, to solve for R1, you want to have R1 is equal to the initial voltage, which is 6, which is this, the given, minus 4, which is what you're trying to get to. And so, and the current, I'll just make it 1 times 10 to the negative 3. And so that's equal to 2K. And so you do this for each one of the resistances. So R2, R3, R4, and R5. And then it kind of follows the same pattern where you're using the previous voltage to solve for the next resistance. So like so. And then 1 minus 0.5, 1 times 10 to the minus 3, and then R5. So the last one is 0.5 minus 0, which is equal to 1 times 10 to the negative 3. And so by doing this math, you're defining the actual values of the resistances that are used to get the desired voltages that are called out in this problem. So you'll be getting 2K, 2K, oops, 1K, 500 ohms, and then 500 ohms. And so once you do that, you have defined these values. You can go ahead and define them in the circuit itself, and then you can build it, which I don't have the setup for. Take my word for it. Okay. So I'm going to switch back to my PowerPoint really quickly. Do you see the screen now?
Yep.
Yep.
Okay, cool. All right, so this is case of finite load resistance. This is utilizing effective resistance formula as well as Kirchhoff's and total current. So V1, in this case, where you see Kirchhoff's current, is the voltage drop across parallel combo. So that's pointed out in the circuit itself. And then so for the derivation, you have to substitute, as you see. And then eventually you get to this formula, which is a bunch of algebra. And that's the formula you would use for a case that would mean that your the current is negligible. So it'd be VL is equal to Vn R2 over everything else. I wasn't going to go too in depth into the derivation. It's mainly just about the end product, but the slides and stuff will be posted for later review if required. And so next is current dividers. What does that even mean? So the output current is a fraction of the input, but also there's a variety of currents in one circuit. And so in this case, they're used for voltmeters and also circuit protection. So I'll go ahead and walk through a current divider example. Let me switch back to my iPad really quick. All right, do you see my screen?
Yep.
Okay, cool. All right, so this is a given formula and you'll be solving for I1, I2, I3, I4, and I5. And it's 1 amp. These are all givens. Sorry, I forgot to include the 1 amp. And so initially you're gonna wanna solve for R equivalent. And so that's kind of just like super basic circuit knowledge. So you'll be doing 20 in parallel with 50. And then I'll just like briefly, it's like 20 and so on. So eventually you're going to get R equivalent is equal to 11.009 in parallel with 100. And so that value is going to get you 9.917. And so why are we doing this? We want to have like a complete circuit that just kind of simplifies the whole thing so we can find total voltage. So you use this resistor and it eventually looks like this, where you have just all of R equivalent in series with the 1 amp source. And so moving on from that, to find the total voltage, you just use V is equal to IR. So you're going to be multiplying V is equal to 1 volt times 9.917, which is equal to 9.917 voltage. Yeah. And then so to find all of the currents that are involved with the formula, you would also use I is equal to V over R, where I 20 is to 9.917 over 20. Which is equal to 0.49, and then I50 is 9.917 over 20, which is equal to 0.19. Oh, sorry, yeah. And then I80, which is using the same formula again and again, becomes 1.23, I120, 0.0826, and then I1, which is 0.099. I didn't need to show all the math because it's just the same formula over and over again. But all of this cumulatively should equal 1 amp added up. Oops. So that's how you like surefire test to make sure that your math is correct. And so going back to my presentation. Node voltage method is also super important. This is used to find V1 and V2, which are the essential nodes. And so this one's important too because you have to know exactly what steps to take to solve it correctly. So I'll step through that as well. I'll switch back. And so in this case, the essential nodes is V1 and V2. They just show that this is the reference to ground. And also in this case, sorry, this is given 25 volts, and this is 3 amps. And so 7 is negligible because it is in series with 3 amps, at least for in this case, we are solving for node voltage. And then so continuing on the math, you define what is V1 and V2. So for V1, you'll do V1 minus 25, because this distance from here to here, you can think about it as like it's going to it, so it'll be negative, over 5, which is the resistance in this part, which is 2 and 3, plus V1 over 2.5, which is V1 over the resistance in that same area. And then plus V1 minus V2 over 10, all equivalent to 0. And so V1 over V1 minus V2 is just describing this relationship between here to here. And then 10 is just what usually is going to be in the denominator to define the essential or the formula. And so you want to equate this. And so eventually you're going to want something that looks like this. But I won't go step by step because that's like simplification. And the main thing is that you want it to be simple enough that you can define it as a matrix. And that makes it a lot easier for solving. And then you factor it. So you'll take out the V1s. So you have a formula that's easier to do a matrix and solve versus having this entire thing is a lot harder and more time. But this is, once you have the full simplified equation, that's like the most important thing, which is this. And then the second part of this you want to do is to define what V2 is. And then with that equation, you'll be able to solve for both of the voltages or essential nodes. So V2, you use the same concept and just focus on this part of the circuit. So you do V2 minus V1, which is describing this relationship here, that distance, over 10, which is the resistance, plus V2 over 5, which is V2 over this resistance here, plus 3, which is the source, is equal to 0. And so you do the same thing again where you want to be able to isolate all of the variables. You want to factor it out. And then so eventually you'll get this equation here. You can get this equation. And so after that, you want to take all those values and make a matrix. So you'll have 7 over 10, 1 over 10, and 5, and then negative 10, 1 over 10, 3 over 10, and negative 3. And you get the values of it's equal to 6 and minus 8. And then so V1 will equal 6 and V2 will equal negative 8, which solves for the essential nodes. And then so I'll switch back to my presentation real quick. The next concept is mesh current method. So in this case, you want to make sure that you label all the mesh currents and then write out the equations individually. And so it's similar to no voltage, except in this case, you'll be more driven on what the current is. And so let me switch back to my iPad. Okay, and so here you'll have I1, I2, and I3. We just want to define those initially so it makes it easier to solve it further down the line. But also in this case, since there's a current source in the middle, there's also a relationship of I2 minus I1 is equal to that current source -4. And this will be important for being able to solve further down the line as well when you get to the matrix part of it. And so you want to define the loops, which we just did. And then so the first relationship you want to describe is I1 plus I2, because this entire thing can be considered a loop. Because by having this equation, it takes care of that part of the loop. So you'll do -10, which is the voltage here, which is given, plus 4i, 1, which is describing here where it's 4 times that current, plus 4, which is the voltage, plus 9 times I2 minus I3, which is describing this relationship here, plus 7 times I1 minus I3, plus 2i equal to 0. And so you want to do the same thing again where you're equating the equation so that you can kind of isolate the variables. So eventually with simplification, you'll get I1 plus 15 I2 minus 16 I3, which is equal to 6. And you do this again for I3, which is this bottom half here, since it doesn't include, since the first equation takes care of all of this stuff, you want to do the next part for this one. And so in this case, it's just I3 that you're worried about. So you do 7 times I3 minus I1, because it's describing this relationship of here, plus 9 times I3 minus I2, plus 12 times I3, which is equal to 0. And so this is just describing the bottom part, again, using the same thing where 12 is times I to the 3, and then again, 9, this is I2 to I3's relationship. And you equate that again to get this formula here. And then so after you do that, you have this formula here, this formula here, and this formula here to solve for mesh current, or for each individual current. But both of them are dependent on each other. You need all of them to be able to solve what you're looking for. And so once you simplify out and make the equations matrixable, you'll have 28, -16, 66, -16, 28, and -36. And so you'll only be able to solve in this matrix I1 and I3. But since you have those variables, you can solve this last equation, which is to have I3 is equal to 0.09, I1 is equal to 2.4. And because you have those both, you can solve for I2, which is equal to -1.6. And so in that case, you're able to solve all of the I2s and I1s and everything. And that's it. That was a lot faster than I anticipated. Are there any questions?
What's an application of a voltage divider?
So you can use it for level shifting, also for adjusting things like radio stations and stuff. But they're commonly found in potentiometers, like variable resistors, stuff like that.
How applicable is this stuff? Like you showed a circuit where like there were like 10 parallel resistors. Would that ever be something that you actually find?
Yeah, especially I see it a lot in the industry where like you don't have the right resistor that you need. And so if you put a bunch of resistors in parallel to each other and like make it the exact resistance that you need, then that's where you would use current divider. Because you would be looking at that R equivalent value.
Do you ever use like mesh currents or Kirchhoff's voltage law during your work?
I've used
Where do you work first
node.
off? Again, like what's your
I work at Northrop Grumman. I'm an intern there, and I've been there for 5 years. I worked initially in radiation test operations. And then afterwards, I worked in materials and processes. But now I work in digital. So currently I'm doing a lot of circuit analysis, but also signal integrity, which is mostly PSpice driven. So these concepts are really critical to understanding how the models that you're making on PSpice work, as well as how to make sure that the outputs that you're looking at are the ones that you want, especially for whatever it is that you're getting it inputted to, whether it's a regulator or a microprocessor, whatever it is. And so it's really critical to understand these really basic concepts, because sometimes like it's the easiest thing that'll be the downfall of your design, especially when it's like PSpice where you're troubleshooting a model and it just doesn't work and it's something simple. So it's really important to know these concepts.
Fair enough. All right. Well, I think does anyone have any other questions for Christina? All right. Well, I think we'll end it there then. We appreciate you coming out. Thank you, Christina. And I'll end the meeting so that everyone can enjoy the rest of their weekend.
Thank you.
Have a good one.